Alright, so today we continue talking about separation of variables. Alright, separating differential equations into a form where you have your x's as a single function, your y's as a single function, times the derivative of y with respect to x and equal to 0. Okay, so that's what we started looking at yesterday. Okay, so we have separation of variables. We can put all x's together, y's together. As long as we got a y prime in there, we can separate and solve. Okay, as a reminder, the way we'll see it most often is more like this, where we have the function of y dy, and then we have equals the function of x dx, and then we'll integrate both sides. Okay, so that's what we're looking for in any situation we see. And as a reminder, we can solve this generally and get a general solution, and we'll have like a plus c or a ce to the something. Okay, that's a general solution. If we want to find a particular solution, we have to have initial conditions. So we have to have some data to find what the constants are. Alright, so here we have example number 4 from 5.7. So here we start with some initial conditions. They're going to ask us to find a particular solution. Okay. The initial condition at 0, y equals 1. Okay, so 0, 1 is our initial condition. And we have this pretty complicated looking differential equation. And it looks really scary. The dx and the dy are already separated. Alright, so we're going to go through the process to try and separate them and solve. Okay. Before we start doing that, we'll go ahead and recognize that what would happen if y was 0? What would happen in this differential equation if y was 0? Look up here. If y was 0, that's 0 and that's 0. Would that be a solution?
Yes. Yeah.
Okay. That would give us, well, that would give us 0 here.
Yeah, 0. Oh, wait. There's 1. There's negative 1.
You would get negative 1 times this
Times
dy. I don't see this. Okay. Why is y 0? Okay. I'm going to go back and look at that. That doesn't quite make sense to me. Alright. Okay, if y is okay, so remember this is a differential equation, and we're looking for, let me get rid of this. There we go. Okay, this is a differential equation. Solutions mean that whatever's on the left side equals whatever's on the right side when we're done with it. A solution would mean if I plug something in, I get the left and right equal. Okay. We'll have to take a look at y equals 0 one more time. But even if y equals 0 is a solution, it doesn't match the particular solution that we're being asked to find. Okay. So we're being asked to find when y is 0. X is 0, you're correct, then y is 1. Okay, so we know y equals 1 has to be part of our solution. Okay, alright, so first thing we want to do is rearrange things so that we have the variables on separate sides. First thing I'm going to do is take the dx term and move it to the other side. So e to the negative x squared, y squared minus 1 dy equals negative xy dx. Now that I have the dy and the dx on separate sides, I can go through and figure out what terms need to go where, okay? What terms on the right side need to move to the left?
What?
Just the y, right? We need to divide by y on both sides. What terms from the left side need to move to the right? This part, right? We need to divide by e to the negative x squared.
Oh, yeah, right.
Okay. All right. Is that all?
Yes.
All right, that should do it. So rewriting here, we have y squared minus 1 dy over y. And on the right side, we have negative x over e to the negative x squared, but if it's negative, we can flip it to the top, so times e to the x squared dx. Okay. Now we go through the work of differentiating. I'm sorry, integrating, not differentiating. Okay, so integral of the left, integral of the right. Okay, now we have to pull out our toolbox of all the different ways we integrate. All right, looking at the left side, what kind of tool are we going to use to integrate this?
First divide each term.
Yeah, it's way easier than you might initially think, right? Just divide each term. That's going to leave you with y minus y to the negative 1 dy. Okay. And then what's the next step?
For this one?
Yep, the integral of y dy is just over 2. Okay, and then what's the integral of dy over y? Ln absolute value of y. Okay, so that's the left side. Okay, feel okay about that? Okay, all right, now let's take a look at the right side. What kind of pattern do we see? What can we use here?
Just E.
We see e,
Yes.
and it's e to the something that's not x. So what process do we probably want to use? U substitution, right? U substitution. So pick a u. U is whatever's in the e, right? So u equals x squared. In that case, du would be what? 2x dx. Now reference back over here. We have an x and a dx, and we've got a negative, okay? The negative is going to go outside, right? And then the 2 we need to divide by. So put a 1/2 out here. All right, and then it's going to be e to the u du. Feel okay about that? All right, so now we integrate that. What's the integral of e to the u du? E to the u plus c. All right, final answer, negative 1/2 e to the, what was u again? X squared plus c. All right, zoom back out, and we got something nice here. Not too bad. Okay. Now, here is our answer. That is our general solution. What makes it general?
Apply all the answer.
Equal 0.
No. What makes it a general solution and not a particular solution?
Or you can put all the value on the left hand and leave the number on the right.
No, we're a general solution because we still have a c.
Oh.
We have a constant, right? It's a whole family of functions, okay? What we want is a particular solution. How do we find that particular solution? Go back and look at our initial condition. Our initial condition says that 0, 1 is a solution point.
We can put the x and the y.
All right, so wherever we see x, we put in a 0. Wherever we see y, we put in a 1. All right, so there we get 1 over 2 minus ln 1 equals negative 1/2 e to the 0 plus c. All right, and we want to solve for c. So 1/2, what's ln 1?
0,
Good. What's e to the 0?
1,
All right. So add 1/2 to both sides, and c equals 1. So our final answer is y squared over 2 minus ln absolute value of y equals negative 1/2 e to the x squared plus 1. And that is our particular solution. Okay. Any questions? No questions? Sure? What's a general solution? What makes the solution general?
have a C.
No C.
A general solution has a C, a plus C, a constant we have to solve for. A particular solution is when we've used our, what do we use to find the particular solution?
Initial condition.
Initial conditions. Sorry, I messed that one up. Okay, good. Okay, let's look ahead at example 5. All right, so now, if you remember, all right, when we looked at general and particular solutions before, we are also looking at slope fields, right? The general solutions are a family of functions, all right, and the particular solution is when you take that family and narrow it down to one particular graph. So that's what we're looking at here. We want to find the equation of the curve that passes through the point 1, 3. What is 1, 3 acting like in this problem?
Particular solution.
An initial condition.
Oh.
All right, that's acting like an initial condition. All right, it has a slope of y over x squared at the point xy. What does that mean? It has a slope of y over x squared at any given point. What does that mean?
The slope is y over x squared.
Yes, but what does that mean in calculus terms?
It's like y equals y over x squared, x plus c.
Y over x squared. What does slope mean in calculus terms? What word do we associate with slope?
Okay.
No?
Derivative.
Derivative. That means the derivative is equal to y over x squared. Okay? So the derivative is y over x squared. That's our differential equation. All right? So here it was a little bit different, right? In the last one, they gave us the differential equation. This one, we had to filter through the words and write our differential equation. You have to know how to do that, okay? So we write our differential equation. All right, now we're going to follow the same process that we did before, though, and separate our variables, okay? So what do we need to do? Let me do it down here. dy dx equals y over x squared. What do we need to do on the right side to get all x's?
Get all x.
On the right side.
Divided by 1.
Okay, so times 1 over y. And we need to multiply by dx also. Okay, so times dx over y. Dx over y. And what do we need to do to get all the y's together? We want to get, oh, that's it, sorry. You're right. I mean, yeah, so 2 steps, we got them all separated. Good. All right, so our new equation is dy over y equals dx over x squared. Now we can integrate both sides. All right. On the left side, what do we get? Ln of y, good, with absolute value. And on the right side, this is the same as integral of x to the negative 2 dx. What's that?
Negative x to the negative.
Yes, negative 1 over x.
Oh, plus c.
Okay, plus c. All right, again, we always want to go ahead and solve for y. So y equals something. How do we get y by itself here?
Initial condition.
Nope. To get y by itself, we use our e. right? E to the function on both sides. So e to the ln y cancels out the e and the ln. We're left with y equals e to the negative 1 over x plus c, and I'm going to do this one more time. Remember, e to the a plus b equals e to the a times e to the b. So in this case, this is the same as e to the negative 1 over x times e to the c. But e to the c is just a constant. E is a number, right? 2.7 something, whatever. So we can just call this c. Okay? So our solution looks like c e to the negative 1 over x. Y equals c e to the negative 1 over x. Now, that's not our final answer because we want to find a particular solution. So we go back and see what is our initial condition. Our initial condition is the 0.13. Okay? So the 0.13 has got to work, so I plug it in. 3 equals CE to the negative 1 over 1. Alright, so e to the negative 1, so 1 over e. Alright, so c is what? Alright, to get c by itself, you got to multiply both sides by e. I'm sorry, that looked like an x, but it's not supposed to be an x. It's a multiply symbol. Multiply by e, multiply by e. C is equal to 3e. Okay. Okay. Weird. Okay. All right, so c is equal to 3e. So our final answer looks like this. Y equals 3e, e to the negative 1 over x. What can we do with those e's?
It's e to the 1 x, or 1 over x. Oh, wait. Without negative 1 over x?
I'm sorry, yes. Negative 1 over x. There we go.
Negative 1 over x. So it's like plus 1. Or e to the x minus 1 over x.
Okay, so this is the same as e to the 1, all right, and so this is 3e to the 1 minus 1 over x. If we want to put that into one single fraction, we would get 3e to the x minus 1 over x, or x minus 1. Okay, all right, that's a final answer that's cute and tidy. And now I know my writing is not that great, but let me fix that. There we go, 3. Okay, any questions on that one? We separated the variables. The key there is that you need to understand when in words it tells you slope, that means you can write a differential equation. Okay? So now we'll take a look at another application problem for differential equations. Again, this is probably one of the most applying type problem you'll see. All engineering majors usually have to take a class called differential equations. So it really applies in a number of different situations. We can use it for a lot of different modeling purposes. All right, so here we have the rate of change in the number of coyotes. You guys know what a coyote is?
Yeah.
Howl at the moon. Ow, ow, ow.
What?
Coyote, it's like a dog.
I don't know that. I thought it's different.
Like this. And they have teeth.
Like kind of a wolf.
Yeah, it looks kind of like a wolf, yeah. Okay. So a coyote, you find them in the desert. Okay. All right, listen. The rate of change of the number of coyotes N of t. So N of t is representing number of coyotes. All right. The rate of change is directly proportional to 650 minus N of t, where t is time in years. When t equals 0, the population is 300. When t equals 2, the population has increased to 500. Find the population when t equals 3. Okay, all right, so it told us the rate of change, but it did not give us a specific equation. We have to write that. If we're writing the rate of change of coyotes, what variables are we going to use? What mathematical language will we use? The rate of change in coyotes in time. What represents the number of coyotes? N. And we're talking about the change in that. So how would we write it?
dn over dt.
Excellent. dn dt. And this tells us it's proportional to what?
Proportional to 650 minus n.
Okay, good. 650 minus n. It's proportional. If it's proportional, remember we can replace proportional with equals if we do what?
Okay.
If we have a constant there, okay? So the rate of change, dn dt, of coyotes is proportional to 650 minus n, so it's the change in the thing depends on the number of the thing, okay? We change proportional to equals if we have a multiply by a constant, okay? Okay. We also have several initial conditions. What are our initial conditions?
0, 300, 2, 500.
Okay, good. So at 0, we have 300 coyotes, so T and N. And at 2, we have 500. And what is it we're trying to find?
1 T for 3, what is n?
Right, okay. So when T is 3, what is N? All right, everything look okay? Okay. Let's take a look. We see we see the variable in our differential equation. Our first step should be to separate the variables, get the dn with the n. So what can we do to do that?
Multiply each term.
Multiply dt.
Okay, divide both sides by 650 minus n and multiply by dt. Get the dt on the other side. All right, so that's going to give us dn over 650 minus n, and on the other side we'll be left with k dt. All right, now we can integrate both sides. What does the left side look like?
Looks like ln 60, absolute 650 minus
Okay.
negative.
Okay, it looks a whole lot like a natural log problem, right? Because we have the degree on the bottom is 1 less than the degree on the top. All right, let's look through that, okay? If the bottom is u, 650 minus n, what is du?
Negative.
Negative dn. Do we have a negative here? No. So negative integral of du over u. All right, and so our integral then is negative ln of what's inside, so 650 minus n. All right, so that's the left-hand side. The right-hand side's pretty straightforward. What is it? KT plus C, good. All right, again, same process we've been doing over and over again. What do we do to get the in by itself? That's what we want to end up with. Okay, raise both sides with the e. Okay. Actually, in this problem, we want to do something else first.
Put the negative to the other.
Yeah, go ahead and multiply everything by a negative, which is going to make the left side positive, the right side negative there. This is negative, but it really doesn't matter because C is going to be positive, negative, doesn't matter. Well, I guess they keep it. I don't know that it should matter, but either way. All right, so that gives us 650 minus n equals e to the negative kt minus c, okay, which, again, that's like dividing by e to the c, which is just another constant, so we'll just put the c out front. Okay, well, it will deviate slightly here. And then if we want to get in by itself, All right, we see some other tricks with, in terms of the sign, right? If we move 650, we're subtracting 650, but then in is going to be negative. We really don't want that. Okay, so if we multiply everything by negative, okay, we'll end up with positive in on the other side. All right, so our final answer, n equals negative CE to the negative KT plus 650. Okay. Looking back at our problem, all right, we want to find the population when t equals 3, so we need to actually solve for our constants. So looking back at our initial conditions, all right, and our newly formed equation, n equals negative CE to the negative KT plus 650, and looking here, when t is 0, we have 300, so negative c e to the 0 plus 65. Okay.
235.
So
It's
c is
negative 235.
Yes.
I wrote that wrong. 650. Sorry.
Oh. Then it's negative 350. Oh,
Okay.
it's 350.
Minus 300 from that side, minus 300 from that side. All right, put this one on the other side so it's positive. So C is positive 350. Okay, and then the next step is to find K. All right, so our other initial condition is that the coyotes, there are 500 coyotes. Now we know what C is. When, oops, that should be a negative. E to the negative K times 1 plus 650.
I think that's a 2.
I think you're right, yes. Okay, that should be a 2. Okay, good. All right, so now rearrange, solve. We all know how to do that, correct? All right, so K is equal to about 0.4236. Notice there's already a negative there. What does that mean? Actually, there's two things going on. There's already a negative there, but there's also already a negative there. So those two negatives essentially cancel each other out. So yes, so it ends up being increasing, which is what we would assume. All right, so once we have our final equation, so n equals 650 minus 350 e to the negative 0.4236t. Okay, now we can find out at t equals 3, n is 552. So it keeps increasing, but not quite as quickly. All right, so modeling populations, again, that's important for a number of different fields, both scientists, economics, sociologists type fields. All right. Okay, any questions on that problem? No? Okay.